Hi, I'm Mira Kuntawala, and this is my Lab 2 on drag force. Drag force was studied by observing and modeling non-constant velocity by dropping an object about 7 feet from the ground and quantifying this data in Tracker and then using those beginning points from Tracker to create a code in VPython using gravity as the source of net force. Comparing the two graphs I got, I saw they did not match up. Going back into VPython, I added in drag force as another component of net force and then saw that those graphs lined up almost exactly. This proving that our model in VPython is a good assumption for drag force. So the fundamental principles that are useful in this lab and experiment are Newton's second law and the momentum principle once again. This is very familiar to us as it is the premise of what we've been learning thus far in physics. Of importance as well are also Newton's first and third laws. Newton's first law being that an object in motion will stay in motion until acted upon by a force, and Newton's third law, which states that for every action there is an equal and opposite reaction. Drag force is an example of a force that causes non-constant velocity, and simply because it is a force acting upon the object, which will affect its velocity. Drag force is any force that impacts an object moving through a medium like air or water, and it acts in the direction opposite of the direction of the velocity. We also know that non-constant velocity will lead to a net force of non-zero. Now let's look at Tracker. I dropped a tangerine about 7 feet from the ground, and it fell in a fairly straight line. As you can see in the right-hand corner, I received a graph of my y position over time and calibrated my axes based on the center of the mass of the tangerine, with the y-axis pointing up in the positive y direction and down in the negative direction. So my tangerine fell in the negative y direction. Here is my Python data. This is the second round of Python, which includes drag force and gravity as components of net force. So things that were changed were the ball's mass was added in the beginning, the ball's position and initial velocity were both put as 0, time step of delta t, what the constant of gravity was, a component of b, which is the constant used for drag force, and then down here we can see the two equations for gravity, for weight force, and for drag force here that added in for FNet. And below are the updated positions, or the updated formulas for Newton's second law and for the position update formula. Here is what the program looks when it was run in Python. Here are the 3 lines of data gathered from Tracker and from the 2 sets of Python code. The blue, which is the Tracker data, matches up very well with the red line, which accounts for drag force and gravity. The yellow line, which only accounts for gravity, veers off to the left and over predicts, mainly because you're only taking into account one force as an interaction. Now, the discrepancies between the red line and the blue line could be accounted for by the fact that my tangerine didn't fall completely straight down, or that the constant I used for B might not have been as accurate or as close as it could have been. Now to address the what does it mean and what if questions. So, which model helps show terminal velocity better? And in my opinion, the model that shows that better would be the one that takes into account both drag force and weight force as forces that contribute to the net force, because terminal velocity is defined as when drag force equals the weight force, and the first model that we created in VPython does not match that because we only accounted for weight force. So for the what if question, what if the object, in my case the tangerine, had been thrown? How would that have affected terminal velocity? Well, adding an extra force, the force of my hand on the object, would be something that changes the net force, and it would also increase the velocity of the tangerine as it fell from my hand to the ground, which would cause terminal velocity to occur at a different point in time. The value of the terminal velocity would remain the same, but it would just be hit at a different time because the object's motion has now changed. Well, thank you for listening, and I hope you enjoyed my lab. Bye.